Suppose I give you the fastest spaceship ever imagined. Not just fast, absurdly fast. Faster than any rocket, any probe, any science fiction engine. I say, we're going to Alpha Centauri. It's only a little over 4 light years away. And you say, great, let's just go really, really fast. Now here's the strange part. Even if you keep pushing and pushing and pushing, pouring in more fuel, more energy, more ingenuity, you will never quite reach the speed of light. You can approach it. You can get embarrassingly close, but you cannot cross it. Not if you are made of matter. And that means something astonishing. It means there are places in the universe that, in a very real physical sense, are forever out of reach within a human lifetime. Not because we lack engineering skill, but because reality itself says no. Why? What is so special about a light year that we can define it, measure it, dream about crossing it, but never actually outrun the light that defines it? To understand that, we have to start somewhere very ordinary. Let's begin with motion. Imagine you're on a train moving at 100 kilometers per hour. You walk forward down the aisle at 5 kilometers per hour. To someone standing on the ground outside, you're moving at 105 kilometers per hour. Simple addition. Velocities stack. That's how the world seems to work. Galileo understood this beautifully. If you're below deck on a smoothly sailing ship, you toss a ball straight up. It comes back down to your hand. You don't feel the ship's motion. The laws of physics don't care whether you're moving smoothly or standing still. Motion is relative. There is no absolute at rest, only motion compared to something else. This idea is so natural that we hardly notice it. It's built into our bones. If I run forward in a moving bus, I add my speed to the bus's speed. If I fire a bullet from a moving airplane, its speed relative to the ground is the plane's speed plus the bullet's speed relative to the plane. That's common sense. And for centuries, it worked perfectly. Then came light. Now light behaves strangely. It's not like a bullet. It's not like a thrown ball. By the 19th century, scientists had discovered that light is an electromagnetic wave. Maxwell's equations, beautiful, symmetric, elegant, predict that electromagnetic waves travel at a specific speed. That speed depends only on the electric and magnetic properties of empty space. And when you calculate it, you get a number, about 300,000 kilometers per second. Here's the puzzle. Maxwell's equations don't say that's the speed relative to something. They just say that's the speed. Relative to what? If you believe in the old picture, there must be some kind of medium, a stuff filling space, through which light waves move. They called it the luminiferous ether, a lovely word, very poetic. The idea was that light travels through this invisible ether, the way sound travels through air. So the Earth must be moving through this ether as it orbits the sun. That means if you measure the speed of light in the direction Earth is moving, you should get a slightly different value than if you measure it sideways. That's just velocity addition again, like running in a moving train. So in 1887, two very careful experimentalists, Albert Michelson and Edward Morley, tried to measure this difference. They built an extraordinarily sensitive interferometer. They split a beam of light in 2 perpendicular directions, sent the beams out and back, and looked for tiny shifts caused by Earth moving through the ether. They found nothing, no difference, no ether wind. Light traveled at exactly the same speed in all directions. That was shocking. Maybe the apparatus shrank slightly in the direction of motion. Maybe time behaved differently. Physicists began inventing increasingly strange explanations to preserve the old idea of absolute motion. Then along came a young patent clerk named Albert Einstein. Einstein did something radical. He asked, what if the experiments are right? What if the speed of light really is the same for all observers, no matter how they move? Let's think about how crazy that sounds. Suppose you're in a spaceship flying at half the speed of light. You turn on a flashlight pointing forward. What speed does the light move away from you? Common sense says half the speed of light plus the speed of light. That would make it 1.5 times the speed of light relative to someone standing still. But experiments say no. The stationary observer still measures the light going at exactly the speed of light, not faster. So velocities don't simply add when light is involved. And if velocities don't add the usual way, then something deeper must give. Einstein's insight was brutally simple. The laws of physics must be the same in all inertial frames, and the speed of light in vacuum is the same for all observers. Those two statements together force the universe into a new shape. If the speed of light is fixed for everyone, then space and time themselves must adjust to make that true. Now we enter the strange territory. Imagine 2 events. A light pulse leaves a spaceship, hits a mirror, and returns. To someone inside the ship, the light just goes straight up and down. It travels a certain distance in a certain time. But to someone outside watching the ship fly by, the light doesn't go straight up and down. It traces a diagonal path because while the light is moving up, the ship is also moving sideways. So from the outside observer's point of view, the light travels a longer path. But here's the key. Both observers measure the same speed for the light. Speed is distance divided by time. If the distance is longer for the outside observer and the speed must be the same, then the time must be longer too. That means the clock inside the moving spaceship ticks more slowly compared to the stationary observer's clock. Time dilation. It isn't an illusion. It's not about perception. It's built into how space and time fit together. And this has been measured. Muons, subatomic particles created in the upper atmosphere, live for about 2 microseconds at rest. Yet we detect them at the Earth's surface. How? Because they're moving near light speed, and their internal clocks tick more slowly relative to us. They live longer in our frame. This is not philosophical, it's experimental. Now let's push further. If time stretches, what about space? Imagine measuring the length of the spaceship as it flies by. You have to record where its front and back are at the same time. But, at the same time, depends on your frame of reference. Relativity of simultaneity enters. When you do the mathematics, and it's not complicated, just careful, you find that moving objects contract in the direction of motion, length contraction. So a fast-moving spaceship is shorter in the direction it's traveling. Now here comes the part that directly answers our question. As you accelerate an object, its energy increases. In Newtonian physics, energy increases because velocity increases without limit. You double the force, you double the acceleration. Keep pushing, keep speeding up. But in relativity, kinetic energy doesn't just increase velocity. It also increases what we might loosely call relativistic mass. More precisely, it increases total energy and momentum in a way that resists further acceleration. The formula for relativistic energy contains a factor. 1 over the square root of 1 minus v squared over c squared. As v approaches c, that denominator approaches 0. And when the denominator approaches 0, the energy required to increase the speed further approaches infinity. Infinity. That's not a large number. It's not a lot. It's unbounded. To accelerate a massive object to the speed of light would require infinite energy, which means it cannot be done. Not because we lack fuel. Not because we lack cleverness, but because the structure of space-time itself forbids it. The speed of light isn't just the speed of light. It's the speed at which cause and effect propagate. It's the maximum speed at which information can travel. It's the conversion factor between space and time. In Einstein's deeper formulation, special relativity unified with space and time, we don't talk about space and time separately. We talk about space-time. And different observers slice space-time into space and time differently depending on their motion. The speed of light is the invariant structure in that geometry. It's like a slope in space-time that nothing with mass can exceed. Let's try a thought experiment. Suppose you could send a signal faster than light. Imagine I send a message to a distant star at superluminal speed. In some frames of reference, that message would arrive before I sent it. Because relativity of simultaneity allows different observers to disagree about the order of events that are separated by faster-than-light intervals. And if information can travel backward in time in some frames, causality collapses. Effects could precede causes. You could prevent yourself from sending the message by receiving it first. Nature seems to have decided that's not allowed. So the speed of light is not an arbitrary technical limit. It is the boundary that preserves the logical consistency of the universe. Now let's return to our spaceship trying to reach a light year. A light year is just a distance. The distance light travels in 1 year, about 946 trillion kilometers. If we could travel at 99% the speed of light, it would take a little over a year in Earth's frame to travel 1 light year. But inside the spaceship, because of time dilation and length contraction, the crew would experience something very different. Distances shrink in their direction of motion. Time stretches relative to Earth. From their perspective, the trip might feel shorter. So here's a curious twist. While we can't reach the speed of light, we can, in principle, cross enormous distances within a human lifetime if we travel sufficiently close to it, because the universe contracts along our path. That sounds almost like cheating. But again, it's not illusion, it's geometry. However, no matter how close we get to light speed, we never quite reach it. The energy cost climbs more and more steeply. Imagine pushing a heavy object across a floor. At first it accelerates easily. Then imagine that as it speeds up, it becomes heavier, and the faster it goes, the heavier it becomes. You push harder and harder, but each extra bit of speed requires vastly more effort. That's what relativistic dynamics feels like. At 10% of light speed, relativistic effects are tiny. At 50%, they're noticeable. At 90%, dramatic. At 99.9%, extreme. And at 100%, unreachable. Photons, particles of light, are different. They have zero rest mass. They don't accelerate from rest to light speed. They always travel at light speed. That's their natural state. Massless particles move at c. Massive particles move at less than c. That's a fundamental divide in nature. Now you might ask, why does mass behave this way? Why does energy couple to motion in this specific mathematical form? That question goes deeper. In special relativity, the quantity that remains invariant between observers is not time alone or space alone, but the space-time interval. It's a combination, distance squared minus c squared times time squared. This structure forces the transformation rules between moving frames, and from those transformation rules, the energy-momentum relation emerges. In other words, the limit isn't an add-on. It's built into the geometry of reality. General relativity extends this picture. Gravity isn't a force in the Newtonian sense. It's curvature of spacetime. Massive objects bend spacetime, and free-falling objects follow the straightest possible paths in that curved geometry. Even there, locally, the speed of light remains the maximum speed. Black holes give us an extreme example. Inside the event horizon, spacetime is curved so drastically that all future directed paths lead inward. To escape would require moving faster than light relative to the surrounding geometry, and that cannot happen. So the light speed limit shapes the structure of stars, galaxies, black holes, and cosmic expansion. Now let's step back and reflect. When we first learned about motion, it seemed simple. Speeds add. Objects accelerate proportionally to force. The universe looked mechanical and intuitive. Then light forced us to revise that intuition, and the revision wasn't cosmetic. It rewired our understanding of time itself. Time is not universal. It is not the same everywhere for everyone. It stretches and contracts depending on motion and gravity. Distance is not absolute. Simultaneity is not absolute. And the speed of light sits at the center of this structure like a keystone in an arch. Without it, the arch collapses. So when we say we cannot reach a light year at light speed, we're not saying our rockets are too weak. We're saying that space-time has a geometry that resists that crossing. But here's something even more beautiful. The limit is also what makes the universe comprehensible. Because signals have a maximum speed, we can define cause and effect. Because there is a universal invariant, different observers can translate their measurements into one another's consistently. If there were no speed limit, physics would lose its coherence. There is something almost poetic in that. The same limit that frustrates our dreams of easy interstellar travel is the one that makes a consistent universe possible. And yet, even within this limit, nature allows astonishing possibilities. If you travel at 99.999% the speed of light, time dilation becomes so extreme that you could, in principle, traverse the galaxy within your own lifetime, while millions of years pass on Earth. From your perspective, distances shrink dramatically, so although we cannot outrun light, we can ride along just beneath its ceiling and experience a universe that compresses ahead of us. There's a subtle philosophical shift here. We often think of limits as barriers, but in physics, limits often define structure. The speed of light is not merely a maximum velocity, it is the scaffolding of spacetime. It defines how energy and momentum transform. It defines how fields propagate. It defines how particles interact. Even quantum field theory, the most precise theory we have, respects this limit. Interactions are local. Fields communicate at or below light speed. Experiments at particle accelerators confirm relativistic energy relations to extraordinary precision. Muon lifetimes, particle collision kinematics, GPS satellites adjusting for time dilation. Every day, your phone corrects for relativistic time shifts so it can locate you accurately. Relativity is not exotic. it's practical, and yet emotionally it remains strange. Because deep down, our brains evolved in a world of slow speeds. Apples fall gently, cars move modestly, even rockets are crawling compared to light, so our intuition whispers, just go faster. But the universe whispers back, there is a structure here you cannot override, and that structure is spacetime itself. So why can't we reach a light year at light speed? Because to do so would require infinite energy. Because as we approach that speed, time and space reshape in such a way that the goal recedes ever further energetically. Because causality would unravel if we could exceed it. Because the speed of light is not a technological challenge. It is a geometric boundary. And that realization is both humbling and exhilarating. It tells us that the universe is not arbitrary. It has deep consistency. It has hidden symmetries. It has constraints that are not negotiable. But it also tells us something hopeful. Even within these constraints, the universe is vast and dynamic. We can approach the limit. We can experience time dilation. We can observe relativistic jets from black holes. We can measure gravitational waves rippling at light speed across billions of light years. We may never outrun light, but we have learned why we cannot. And that understanding is, in its own way, a kind of journey, one that carries us across conceptual light years. From the deck of Galileo's ship to the curved spacetime around a black hole, the physical light year may remain unreachable at light speed, but intellectually, we have crossed it. And that may be the most remarkable voyage of all.